now let us proceed to the derivation of the differential energy balance equation in terms of enthalpy and then later on in terms of temperature. Okay. Now, we start with a relationship from thermodynamics. This is a well known relationship which relates enthalpy to internal energy. Like to mention, H cap represents specific enthalpy. Okay. So, it is on a per unit mass basis. Of course, internal energy U cap we know it is per unit mass, and then pressure and volume V cap is also per unit mass basis. Okay. So, we have been working in terms of rho. So, we will express the right hand side in terms of rho. So, we have U cap plus P by rho, V cap is 1 by rho. Okay. The specific volume is equal to 1 by density. Okay. What we will do is express this relationship in terms of substantial derivative, or saying it the other way, we take the substantial derivative of this equation both on the left hand side and the right hand side, that is what we have done here, and of course multiply by density. So, take substantial derivative of left hand side, multiply by rho, we get this term. Right hand side, take substantial derivative, first term is internal energy. So, we have du cap by dt, multiply by rho, second term d by dt of P by rho and then multiply by rho. So, take d by dt on both sides, multiply by rho. These two terms are simple. Let us see how to evaluate this term. Just use product rule. So, rho and then we have 1 by rho dP by dt, and then we have rho outside and then P into d by dt of 1 by rho, and that we get a minus rho square in the denominator and then d rho by dt. Now, to proceed further, we will use the equation of continuity. From a material particle viewpoint, d rho by dt is minus rho del dot v. We know del dot v is sum of all these gradients of velocity. So, we will substitute for d rho by dt in this last term. So, we got minus d rho by dt. So, we get a plus here, and rho squared and rho they all cancel, leaving us with P into the sum of all the three gradients of velocity. So, let us substitute in this equation. Left hand side we have rho dH cap by dt, right hand side we have rho du cap by dt, and then this term becomes dP by dt, and the last term we have seen here, we will substitute that here, P into sum of all the velocity gradients. Okay, so, let us write down the equation which I have derived for the substantial derivative of enthalpy. Now, we have already derived the differential energy balance equation for internal energy, and that is what is being written now, so that we can substitute this on the right hand side. So, let us substitute. Left hand side is rho d by dt of enthalpy. So, we are substituting for rho du cap by dt on the right hand side. So, we have got this term here and we have got this term here, and then these two terms are here. And these two terms cancel each other, leaving us with these two terms only. Okay, so, we have rho dH cap by dt on the left hand side, and then the rate of heat input term, and then substantial derivative of pressure. The first time we are coming across substantial derivative of pressure. Okay. Also like to mention, we discussed about substantial derivative in the very beginning of the course. There it would have appeared as if we are suddenly discussing a new derivative. Of course, we discussed the physical significance, but now look at the utility of that substantial derivative. We are using the substantial derivative very frequently, especially in the derivation of the differential energy balance equation. Not alone that, when we introduced, we said we have substantial derivative of velocity, temperature, concentration, etc. But now look at the derivations. We have substantial derivative of all the energy terms, we have for internal energy, we have for enthalpy, we have also got for pressure. So, significance is same, the variable for which the substantial derivative is expressed, that changes. Okay. So, it does have wide application in terms of derivation and the corresponding physical significance. So, now we will be really convinced the discussion on substantial derivative in the beginning part of the course. We have been looking at limited scope, we have come across only d by dt of density for the continuity equation, d by dt of velocity we have come across, but now the derivation of energy balance we have come across substantial derivative of different variables, energy, pressure, etc. Okay. Okay, now we are towards the last step, we are going to express the energy balance equation in terms of temperature. Okay. Let us do that. Once again we are going to use the thermodynamic relationship. What is that? From thermodynamics we know that for a pure species the enthalpy is a function of temperature and pressure, and this equation we will derive in a thermodynamics course when we discuss fundamental property relations, where we discuss Maxwell relations, etc. We discuss this, we derive this relationship. What does it tell you? It relates the differential change in enthalpy to the differential change in temperature and the differential change in pressure. What is the utility? This expression can be used to find out change in enthalpy if we are given change in temperature and pressure. That is the use of this equation. Now, once again we will express this equation in terms of substantial derivative. Okay, let us do that and multiply by rho. So, this expresses differential change, that differential change could be expressed in with respect to any variable. Now, we are doing that with respect to d by dt. So, left hand side we have dH cap by dt multiply by rho, right hand side we have Cp dt by dt multiply by rho, and then the other terms we have the specific volume expressed as 1 by rho here, and then this tells you the change of specific volume with temperature at constant pressure, that is the significance of that term. We will express once again the specific volume there in terms of density 1 by rho, and we have dP by dt and then of course multiply by rho. So, the thermodynamic relationship has been expressed in terms of substantial derivative, number 1. Number 2, the specific volume has been expressed in terms of density, we have multiplied by density both the left hand side and right hand side. Now, let us take this term multiplied by rho and simplify that. So, we have got minus rho T dou by dou T of 1 by rho at constant pressure, and if you differentiate this dou of 1 by rho, you have a minus becomes plus and then 1 by rho squared, and then we have dou rho by dou t. Now rho cancels, we have one rho left out in the denominator. So, we will write as dou rho by rho. We have got temperature in numerator. So, write the denominator as dou T by dou T at constant pressure. So, numerator becomes nicely dou ln rho, denominator also becomes nicely dou ln T at constant pressure. So, this term rho into that term including the minus sign is dou ln rho by dou ln T at constant pressure. So, tells about effect of temperature on density, but it is not dou rho by dou T, tells about change in ln rho for change in ln T. Okay, now let us substitute that in this equation. Left hand side we have rho substantial derivative of enthalpy, then of course we have rho Cp dt by dt, and this becomes unity, and then this term we have simplified as dou ln rho by dou ln T at constant pressure, and then of course we have dP by dt. In the previous step we have derived the energy balance equation in terms of enthalpy. So, on the left hand side we will substitute the substantial derivative of enthalpy in terms of the thermodynamic relationship which you have seen now, okay, and that is what we will do now. So, left hand side I substitute this relationship which you have derived just now. So, rho dH cap by dt is expressed in terms of rho Cp dt by dt, and then this becomes just dP by dt, then of course we have this term here multiplied by dP by dt. The right hand side we have the terms from our differential energy balance equation for enthalpy. Now let us simplify this and just rewriting the same equation here. That is the left hand side and that is the right hand side. That right hand side is same as what we have seen earlier in the differential energy balance equation for enthalpy. So, now dP by dt cancels on both sides, and then we will express the equation in terms of dt by dt. That has been our long standing objective, to get a differential energy balance equation in terms of temperature. That is what we have done sequentially. So, left hand side is rho Cp dt by dt, right hand side we have the rate of heat input term, and then this I have taken to the right hand side, and that becomes minus dou ln rho by dou ln T at constant pressure multiplied by dP by dt. Also like to mention the Cp is in terms of mass units, it is on a mass basis. So, it is SI unit, it is joule per kg per Kelvin. Okay. More formally we should use Cp cap, just to avoid a complex nomenclature we are using Cp. Okay, let us expand the substantial derivative. We already have derived the energy balance equation. We will by expanding the substantial derivative, we have the local term and the convection term, and this is the dt by dt which we took as an example way back when we discussed substantial derivative. When we first time when we introduced substantial derivative, we discussed in terms of velocity and in terms of temperature. Now you really see an application, or you see a conservation equation where the dt by dt occurs. Okay. So, rho Cp and then the substantial derivative expressed in terms of its two components, and right hand side the same terms are here. Of course, you can also put in a vector notation. So, left hand side rho Cp dou T by dou T, and we know this can be expressed as V dot gradient operating on T, and this we know can be expressed as minus del dot q vector. What is that q vector? Q vector is the heat flux vector. We will discuss more on this shortly, which we can express as qx I heat flux vector due to conduction, qx I qyj then qz k. Qx, qy, qz are the components of heat flux vector along xyz direction. So, this becomes del dot q. Of course, you have minus sign here, the second term appears as such. So, we have finally achieved our objective of deriving a differential energy balance equation in terms of temperature. Now, we are in a situation similar to what we were after deriving the linear momentum balance equation. Okay. What is that situation? Let us see. Let us have a recall slide. This is the slide which we discussed after deriving the linear momentum balance equation. We listed the continuity equation, we listed all the linear momentum balance equations in the three directions. We also expressed the equation of state as density as a function of pressure and temperature. Then we did a degree of freedom analysis, listed the number of independent variables. Rho is one variable, 3 velocity components is 3 variables, pressure is one variable, and then we have 6 independent components of the viscous stress tensor. So, they add another 6 variables and gave us 11 independent variables. Number of equations, 1 mass balance, 3 linear momentum balance, 1 equation of state, and which was 5. Number of equations was 5. So, when you subtract, you were left with 6 degrees of freedom, and we concluded that the components of the viscous stress tensor are unknowns, and to close the system of equations we need to express those components in terms of velocity, velocity gradients, and we call this as a closure problem. Now, we are exactly in the same situation now. If you view them as later on when we started the transfer phenomena part of the course and we discussed momentum transport, we interpreted tau as molecular momentum flux. So, if you want to restate this from that viewpoint, we can say that need to express molecular momentum flux in terms of velocity, velocity gradients. Both are two different viewpoints. The second viewpoint will be more useful because we are discussing about heat flux. Okay. Now, we are in the similar situation now. Let us see why is it so. Let us list down all the conservation equations which are derived so far. We will express from a material particle viewpoint. Okay. So, that is the equation of continuity. The linear momentum balance equation in the x, y, z direction written in terms of substantial derivative number 1. Number 2, right hand side I have already substituted for the viscous stresses or the molecular momentum flux using the Newton's law of viscosity, and so what is shown here is the Navier-Stokes equation, not the linear momentum balance equation, and that is the energy balance equation which we derived just now in terms of temperature. We also require a equation of state expressing rho in terms of pressure and temperature. So, these are all the equations which we have now. Let us do a degree of freedom analysis. What are the number of independent variables? Like earlier, we have rho as one variable, 3 velocity components adds to 3 variables, pressure is one variable. Earlier we had the tau as 6 variable, because they have expressed in terms of the Newton's law of viscosity, they are not the variables now. And what are the other variables? The energy balance has temperature in it, so that is another variable. Energy balance has this components of heat flux vector due to conduction, and they add 3 components qx, qy, qz, resulting in 9 independent variables. What are the number of equations? 1 mass balance, 3 Navier-Stokes equation, okay, not linear momentum balance equation. We already substituted the Newton's law of viscosity. 1 energy balance equation, 1 equation of state, resulting in 6 number of equations. Let us subtract, find the degree of freedom, it is 3, which means that the 3 variables are unknown. What are 3 variables? The components of heat flux vector in the x, y, z direction are the unknown variables. So, analogous statement, just like we saw in the previous slide, what is that? Need to express the heat flux in terms of temperature gradient. That is why I said in the previous slide, the interpretation of tau in terms of molecular momentum flux is more useful now, and we said molecular momentum flux has to be expressed in terms of velocity gradient. Analogous statement now is need to express heat flux in terms of temperature gradient. Okay. So, very much analogous. Okay, let us summarize what we have discussed so far. We have derived the differential energy balance equation through a series of stages. First, we expressed in terms of internal energy plus kinetic energy plus potential energy, which is what we discussed in the previous lecture. In this lecture, we took the effect of gravity from potential energy on the left hand side to work done on the right hand side, so that we could get a differential energy balance equation in terms of internal energy and kinetic energy. Independently, we derived an equation for kinetic energy from linear momentum balance equation, subtracted these two and got a differential energy balance equation for internal energy. Used thermodynamic relationship between internal energy and enthalpy and got an equation for enthalpy, and then once again used a thermodynamic relationship between enthalpy and temperature and pressure, and finally arrived at the differential energy balance equation in terms of temperature. Towards the end, we discussed the closure problem. What is that? Need to relate heat flux to temperature gradient.